welcome. This time we're doing sort of a different thing where we're giving a bunch of lightning talks instead of the longer ones. But either way, I'll be talking to you about Rust. Rust is a programming language. So around 6 years ago, maybe, I found Haskell. And I was still a kid and innocent, and I got blew away by sort of the elegance combined with the practicality, right? So it wasn't just like a research language. It was also like you can do stuff with it and it performs well, and it's really nice. Since then, I haven't found anything like Haskell in having those two properties until I just found Rust. Rust is the same thing. So it takes a bunch of other research languages, like say Cyclone and various other ones, and makes it a practical language. So what it's bringing to the table is a bunch of new stuff from the research land and making it practical. It's really nice. So in particular, I already have Haskell. Why the hell would I use Rust, right? So what Rust brings is the combination of these two things. So control and safety. Haskell gives you safety, doesn't give you very much control necessarily. So I can elaborate on what that means. What is control? Well, one thing that is control is your evaluation. Haskell is lazy evaluated, which is sometimes difficult to reason about. But if all we wanted was strict evaluation, we could just use OCaml. So that's not it, right? The other thing it gives you is full control of the memory layout. So if you look at these two things, you're like, how is this any different from like C or something, right? Well, safety. Use the types. What Rust gives you is so they realize this really deep insight, I think, that the thing that causes memory unsafety is when you have this combination of aliasing and mutation. So say you have two pointers to something, and you can mutate both of them. So one place mutates like it frees that memory. It can update its own pointer to that, but then the other pointer is just hanging out, and you have dangling pointers, right? And similarly, double freeze and other stuff, it's these two properties that cause them. So what Rust does is it uses the type system to never let both of those things happen at the same time. And finally, Rust is modern. And what do I mean by that? Well, it encourages immutability, which is nice. It has a great concurrency story, and it has things that we love, like algebraic data types, Lambda expressions, higher order functions, parametric polymorphism type classes. You would think that most modern languages created recently would have these things, but they don't. Go. Okay. Okay, so let me talk a little bit about, I'm kidding about hating Go, by the way. It's nice too for other reasons, but okay. So let me talk a little bit about how it actually pulls off this safety and control at the same time. So here are three different ways to define a function. Like this would be the header of the function. So in the first case, there's no ampersand before t, which would be the type. The second case, there is an ampersand. The third case, there's an ampersand immutability. So the first one corresponds to passing by value. It does like a byte copy of whatever you pass in. And in particular, at the call site, so each of these behave differently at the call site, okay? So in the first case, at the call site, you would no longer be able to use the thing you pass in after you call the function, okay? I'll explain why you might not want that. In the second case, you pass it, and while that function is running, you can no longer write, okay? So in the second case, you can read, but you can't write, and then when the function returns, you can read and write again, okay? In the third case, you can't read or write while the function is running, but when you get it back, you can read and write again, I'll elaborate more. Okay, so here's the first case. So this is the call site. We define some mutable variable a, and obviously before you call the function, you can read and write it. When you call the function, from that point and on, you can't read or write to a anymore. Okay, so basically it gives away that memory to the function, and you don't get it back. So in particular, if we think about these two things, there can't be any aliasing here because at that point you own it, and then at that point the other function owns it. There's only ever one pointer. And mutability, yes. Yep.
So does it really do a byte copy then? Because it seems like the semantics of this would be so that you don't have to do a byte copy.
Yes. So that is a good point. It does do a byte copy. In particular, the reason it does a byte copy is because I think when there are pointers inside the structure,
okay,
then you would want to do a byte copy.
Yeah.
So here's another example. In this case, we're talking about the ampersand version, and I just made it use two parameters so I can demonstrate this a little better. So we're doing the same thing. We define a mutable variable a, and then we call this function. So now we're passing a reference to a, right? And in particular, after we pass the first reference, we can then pass it again because we can read and share from a at this point. So in the previous example, if this f took two parameters, we wouldn't be able to pass a again because we already gave it up the first time. Okay? But in this case, we can still read from it after this point, and after this point we can read and write again. So in this case we have aliasing, but we don't have mutability in this area. So after this point you only have a again, right? So there isn't aliasing anymore, which is why we can write to it again. And finally, this is the mutable one. So in this spot here, you can't read or write a, but after f, you can read and write it again. So in this case, you don't have aliasing, but you do have mutability. And this one doesn't do a byte copy, just passes the pointer. Okay, so that was a very fast run through, but there are a lot of good resources if you want to learn more. In particular, the first one is Rust for functional programmers. What that does is, hey, you basically know all these modern concepts, let me just give you the different syntax for them. The second one is guaranteeing memory safety. It goes in far more detail about what I was trying to quickly explain there, and it's really nice. It's a video talk. And then there's the official guide and reference if you want more detail, and Rust by Example, which is a very nice site, which I think we should also have for Haskell because it's very nice if you try it out. And yes, you can find these links from that page. I assume maybe I can take a question?
Yeah, you only took about 8 minutes. So
Oh, okay. Well,
if you want to take
yeah, questions.
Fine.
Yeah, sure.
So are those failures if you try to pass a twice without any of the ampersands? Are those
That's a type error. It's a compile time error. Yes.
So I've seen a headline discussing another really compelling feature of Rust about control of resources, like maybe even to the extent that like pipes or conduit gives you sort of very close control over resources, so you're not leaking anything. I don't know what it's like.
I'm not sure particularly what you're referring to. Certainly when you're talking about memory, it's like this is the abstract model here is basically the same as C, right? So
Like file descriptors and stuff.
yep, file descriptors. Yeah, so the standard library has been changing a lot. So I'm not sure the exact story right now. I know they were building, like they're in the process of building Nginx type performance stuff into the standard library. I'm not sure if that's actually been completed or not, but it's getting there, and it should, in theory, be quite possible because of how low level things are.
So if Just thinking about concurrency.
Yep.
And so if I spawn a function in one thread that is holding one of these mutation locks on a piece of data, then how am I going to statically enforce that I'm not going to touch that? I'm not going to mutate that data until the function is done. Do I have to join on the thread? Does the thread have to terminate? What's the story there?
Okay, so this question probably comes from me going through this too fast. So what I was talking about this ownership and things taking, I was using functions to show things grabbing ownership. But it's really about scope. So like if you have a let block, or a block inside of your function where you define a variable and it goes out of scope at the end of the block, that is the relevant, that lifetime there is the relevant thing for determining if you have like two things pointed at, like if you have two aliases to something at the same time or not.
Okay. So this isn't going to change the problem of having multiple threads trying to mutate the same thing.
Right, it doesn't fix that, but it makes it easy to fix that with only a couple more abstractions.
Okay.
So there's something called ARC in the standard library, atomic reference counter. So you need some runtime reference counting to make it work nicely. But what that does is, if I remember correctly, it's a variable which you can only get the shared references from. There's another construction where you it's a mutex, so you call mutex.lock, and what that gives you is a mutable variable back, and the destructor unlocks. Okay, so when it goes out of scope, it unlocks. Since it's a mutable variable, there's only ever one, right? So you use that property to make it work out nicely.
Cool.
Yeah, that was a little fast, but any other? Yeah.
So you said the thing is polymorphism. Does it have higher order polymorphism and higher kind of types?
Not yet. I think that's so. What I'm showing here is the syntax for Rust 1.0, which is they're finally like standardizing and like now's the time to get in. I think they have higher kinds for a later version. I don't think that it's in 1.0. Any other questions? All right.
Thanks.
Yep.
Hey, guys, for speakers, since we're sort of going really quickly, if you want to introduce yourself, go ahead. Because I don't really want to do it for you. I mean, it's not that I don't want to, it's just something.
Sorry, what were you?
This is going to work for me. Okay, at least. There we go. Wait, light? Okay.
What's happened?
Uh-oh.
Don't do it.
Japanese curry powder.
Yes. So let's try this again and hopefully it'll work.
Nope. Does it work when you're not plugged in?
Well, it should. I mean, it worked earlier.
Right.
And it. Okay, so let me just go through it like this.
I don't know about people in the back, but I can see it fine.
Okay.
Is that all right back there?
Can everybody see it? Good. So I'm Elliot Stern, and I'll be talking about phantom types. So to start out with, what's a phantom? So a phantom is a data type that has a polymorphic type variable that isn't actually used in your data. So in the first foo, it's just a wrapper around a string, and we're not actually using that A anywhere. A could be whatever we want. And in the second one, we're using the A, but we're not using the B, so the B is a phantom parameter. And so when you first look at it, you might be like, well, what's the good in that? And the answer is that we can use that phantom tag to constrain the particular types of values that functions take. So for example, if we're dealing with user input, we don't want little bobby tables to cause all of our data in our database to just go up in smoke. So we might want to say that in order to actually write to a database, we need to write validated data back. And how we do that is we have a user input type that has a type variable A, and that type variable is either going to be validated or unvalidated. And so if we want to write to the database, we need to pass in a user input of validated. And when we get data in from the user, it's going to be a user input of unvalidated. And then at some point, we need to have called the validate function. And by dint of this whole thing compiling, you know that if you read and write, you have to have validated at some point in the middle. You can't get from one to the other without having gone through the intermediate state of validating. And that's nice, because you statically know little bobby tables isn't a problem for you. And one thing that I'd like to mention here is that phantom types can be used in any language that has generics. You can use it in Java, you can use it in C++, you can use it in C#, you could use it in Rust. It's a pretty general technique, and I assume that most of you guys probably do not use Haskell in your day jobs, right? But you can use this in your day jobs. And this right here is an example in C#. And so one of the important things here, if you're using this in a language like C#, is that whatever the state is that we're tagging our type with has to be read-only. If we have a mutable string inside of this user input, then we run into the problem of we could validate it, but without actually updating our phantom tag. We need to have separate functions inside of a utilities class that would have our validate function and our read function and our write to database function that take the constrained values. So one question that you might have at this point, just with the example that we've shown, is why not just use a new type? Have a validated new type and an unvalidated new type. Well, one reason for that is if you're using something with a phantom, then you can have functions that are polymorphic over the choice of phantom. So for example, you can have an append function that's polymorphic over your choice of validated or unvalidated, because it's kind of stupid to write that same code multiple times as boilerplate each time. Additionally, you can put a phantom tag on anything you want, including a record, and I'll actually show an example of that later on. So you don't necessarily need to have a wrapping type around whatever your value is. It can just be on your record or whatever. So it can also have simpler syntax. It's also closely related with GADTs. This right here is the user input example. from earlier. And the nice thing about GADTs is that you can constrain those constructors there, so that way the only possible values that you have there are the user input of validated or the user input of unvalidated. Previously, you could have a user input of int if you wanted, because it's just a free type variable, and you can write a function that'll instantiate that with any particular type variable you want. So it's non-extensible, which is to say we just have the validated user input and the unvalidated user input case. And that's good or bad depending on whether you want to know the entire universe of everything that you have, or if you actually need this to be extensible at some point later. With something like this, it's probably okay to have it be unextensible. You're probably not going to have a possibly validated case, or something like that later. The other thing is with what I mentioned earlier about the polymorphic functions. We now need to pattern match on the validated UI case and the unvalidated UI case. And that means that our polymorphic functions have additional boilerplate. So that's kind of a drawback. But the nice thing here is that the GADT kind of requires this whole construction to be correct. So you can just like export your user input type, whereas with phantoms, it allows you to write an implementation that's correct by default, and then you'd only export that implementation. So your smart constructors like read or like make validated and make unvalidated and that sort of thing. But you wouldn't want to export just the base user input type, because you can do unsafe things with that. Yes?
You can also do that with the GADT. I mean, if you export the constructors for this user input type, then I could just pattern match on the unvalidated UI constructor and then wrap that string back up in a validated UI constructor. Like I could write my own fake validate function.
This is true. Yeah.
So
It's-
encapsulation with smart constructors is necessary in both cases.
Right.
Yeah, I guess I would say that GADTs maybe give you the ability to help prove that the implementation is correct. Just using them doesn't necessarily guarantee that, but you might be able to do that.
Yeah,
With
that
a
is
lot
a
of
good
work.
point. And now I'm going to go into a couple of examples. And there's a technique that seems to be mostly unknown in the Haskell world, but more well known in the ML world. Why does this thing keep popping up? Which is...
Turn the internet off, it might stop.
This is a good point. So, if you have your phantom tag itself have a phantom, you get something that's kind of similar to subtyping. So this case right here is actually straight out of the Standard ML of New Jersey's standard library. Our socket is just a wrapper around a int, like it is in C. It's just whatever the address is of the socket. And then we've got a type there. And that type is either going to be UDP or TCP of A. And then that A there is going to be either passive or active. Where passive means that we're waiting for a connection, and active means that we're actively connected to a remote socket. So the subtyping is that we can write a function like close that can take any kind of socket and, well, close it. We can write a function like Nagel that takes any kind of TCP socket and says whether we're going to use Nagel's algorithm on that socket. Or we could write a function like listen that takes a passive TCP socket and says that we're going to set up a buffer to listen on. So this right here is not really something you could easily do. using new types. Have this kind of subtyping relationship between your functions and values there. And then another thing that we actually use at work is with some functions, like for example making a chart, you have a lot of optional things that you might want to do. For example, setting a format for the x-axis or a format for the y-axis, saying, for example, that the string there is going to be rendered using markdown or no markdown, or it's a number and it should be rendered as a %, or it should be rounded to a certain level, or we might want some sort of label on the x-axis or whatever. So we've got this thing for kind of default and named arguments, where what you do is you have a record that contains all of your default arguments. And that record has a phantom parameter. And then we've got a value, default chart options, that is just all of the default values. A standard, just display this normally format for both of the axes, don't give it a title, etc. And then the interesting thing is that with default and named arguments, you can't give a argument twice to a function. That really doesn't make much sense. So what we want to do is say that you can only set the argument once. And the way that we do that is the phantom parameter is actually a tuple containing either bound or unbound for each of the things that's in our record. And then we have a bunch of functions, y format, x format, title, whatever, that for the phantom parameter are kind of free in all of the other variables. So this x format here could be either bound or unbound when we're calling y format. Title can be either bound or unbound. But the variable that corresponds to the y format needs to be unbound here. And then when we set that, we return back a chart options where it's bound. So that way, when we're chaining together these functions from chart options to chart options, you can't call y format twice. And then finally, our chart function here takes a function from a chart options A to a chart options A prime, which would be, for example, x format %.y format markdown, and then it takes all of the arguments that you actually need to take in order to generate a chart, and then it returns a chart. So in this case, the kinds of axes you have, as well as the actual data that you're using to make this chart. So using this, instead of taking a bunch of or a dozen or so maybe parameters, we instead just take that function there, and we can set maybe a couple of things and not have to worry about all of the other parameters that we don't care about in this case.
It seems like it's at the expense of the library designer, but the users greatly benefit.
Exactly. The library itself here is a lot more verbose, but calling this is really nice. And I think actually this thing is was thought up of by Paul Chisano, who I don't believe is here. And I was asking around work. That seemed to be the person responsible. And
You have about 2 minutes.
yep, so that's about it. I've got a couple of papers here. If people are interested in the subtyping thing, you can take a look at this paper here, which actually tells you how to encode any random subtyping hierarchy, including things that aren't just trees but actual graphs. And does anyone have any questions? Yeah. Yes?
One thing that you can do to make this sort of presentation even nicer is to use the Data.kiln extension to limit the kinds of things that you can have as a particular phantom type. So you were talking about incoherent things like user input int as opposed to validated or unvalidated. So you could have a sum type and then just lift that up to the type level and restrict the kind of your phantom type variable, and everything works out really nicely.
Exactly. And actually one thing that you can do in Java and C# now is you can do a similar sort of thing where you say that your type parameter A needs to be a subtype of some particular type, in this case, validation status. So that's exactly the same type of thing as you can do in Haskell now with the data kinds, just in C#. Anything else?
Thanks.
Oh.
Probably would have heard. I didn't hear him.
Yeah, true.
That went well.
Okay, cool. Maybe I'll just text him. He may have just forgotten.
Can you post up your slides?
Hello everybody, my name is Will Blair. I'm a graduate student over at Boston University where I pack on the ATS programming language. And ATS is a statically typed functional language like Haskell, but more similar to the ML family of languages. And I'd like to talk about it here today because, one, if you're at a Haskell meetup, you guys are all probably fans of statically typed functional languages. But also to just kind of demonstrate one reason why you might want to use ATS in a project. And I don't have like a lot of slides prepared, but I'd just like to kind of discuss how you could go about debugging a certain kind of program using ATS. So the idea that I'm thinking of is that, you know, when we're writing functional, a lot of functional code, the type we work with a lot is your simple list, right? A list has some type A, and in ATS we have this a kind of strange convention of distinguishing between types and what we call flat types. So in a lot of languages, like say in Java, most types that you work with are boxed, right? Because they point to some container that has the actual value. But when we're working at a low level like C, everything is either a primitive value or a flat structure, right? So in C, we have, in ATS, we share C's native unboxed representation of data, and that allows us to work with types that have varying different sizes. So when we say a data type contains a list, we say that the list has some region of memory that's the size of any type A. And so the hint there is that this is driven by templates, and when we write functions over lists, we'll be instantiating templates for that type. So this is, that's just some boilerplate to try to introduce the example I'd like to work through. So when we have this basic data type in ATS, I mentioned earlier we share C's native representation of data, but that's not very convenient when you work with something like immutable data structures like lists. You want to just be able to cons elements on top of each other and not worry about the details of how that memory is being allocated. And in order to do that, we provide the data type, which are strictly boxed data. So the whole idea is that the programmer doesn't control the memory that is taken up by these lists. Instead, it's controlled by a garbage collector. And so when you work with these, what we kind of refer to as nonlinear types, and I'll explain the term linear in a moment, you don't have any control over how the system uses the memory for these lists, or for these like algebraic data types. So if you wanted to implement, for instance, a very simple append function, which would be like most functional languages, you're given two lists and of some type A, and you want to produce the append of those two. Well, this is some very simple code, but it's kind of, it's not necessarily inefficient because it will allocate a new list that is just the appending of XS and YS. But now we have 3 lists in memory. And with just a box data type like list, we can't really dictate, well, what if we don't want these 2 lists after append is called? What if after I call append, I just want 1 list that is the append, that is the concatenation of YS onto XS? So if I were to run this example in a very simple main function, let's say I just generated 2 random lists that are both blank 10,000 and put them together, you might, what would we expect the heap to look like at the end of this program? We would imagine, because if we have a conservative garbage collector, or we don't even have to think about a conservative garbage collector, at the end of, once we get to this point, we have 3 variables that are in scope, right? We have XS, YS, and then RS. So at this point, a garbage collector couldn't just get rid of XS because it's still in our scope. And so if we were to run this, let's say, and then chart how memory is used on the heap, we'd get something very linear, which we would expect, right? Because all we're doing is adding memory up together and not actually freeing it explicitly ourselves. And in that very simple program, where we just have 3 variables, all we're kind of doing is adding on to the heap. But, as I said earlier, what if we want a version of append where we explicitly state that those the 2 initial lists, XS and YS, should be removed. They should be consumed by append. And so in ATS we have what we call linear types in order to model this resource consumption. And so that you could actually explicitly state how resources are used in your program. So if I were to go over to a slightly different version of list, we see something that's not much more complicated, but we have what we call the data view type. And what data view type means is that any type of list VT is now linear. And when a type in ATS is linear, it means the programmer must, at any instance of it being used, prove that it will be eventually used or consumed in the code. And what that means is we have various ways to describe how linear types are, or how linear values are consumed. If we go back to append, and if I want to say that XS and YS are consumed by append, all I have to do is list them right here. There's another form, like what if I wanted them to be preserved after the call? The modification I could give to the type signature would be something like, would be this. And it's long been a point of contention about the syntax of ATS that this is kind of confusing. That an exclamation mark means preserved. But what this means is that append preserves XS and YS and also produces a new linear list. So when you call append, you maintain a view, to borrow the term from data view type, you maintain ownership of XS and YS, but you also obtain a new list. Oh, yeah, go ahead.
So you can't choose at the call site.
Oh, you can't choose explicitly at the call site. It's kind of built into the, you have to give a type signature.
I see. Okay.
So you can imagine, that's a good point. So if I wanted to say, if I wanted to like pass to append and say, you need to consume this.
All right. I want to keep X's around for later, but I don't need Y's anymore.
Oh, okay. Yeah, in that case, you would need to, you would have something like this, and you would have to change. You have a specific version of append.
So you'd have to have like the powers of append if you wanted.
Right.
All
Yeah.
possibilities. Okay.
Yeah, that would be, that would be kind of tedious to do. I don't think you could like explicitly say at the call site, you are now responsible for this. Yeah, go ahead.
Well, in this case, I mean, with append, you can't get rid of Y's in any case, right? Because U is part of your list.
Oh, which one?
Y's.
Sure. I mean,
To get rid, like when we say we get rid of it, we don't have to necessarily free it. Instead, that's a very good point. We're not consuming YS. Instead, YS is a part of this linear list. So when I say that you have to consume the linear value, I think that might be somewhat incorrect. Because you don't necessarily have to free both XS and YS. The only requirement that is placed on append here is to return a new linear list. So you can imagine a very incorrect implementation of this to basically a fool implementation would be to just return nil and then free both xs and ys. But yeah, you're exactly right. We don't necessarily have to free ys. Instead, we kind of pass it back to the caller, and then the caller is then responsible for ys. But that, I guess that's also in recursion there. Oh yeah?
So because we're using ys in the return value, can you preserve it? Or is the fact that it's inherently subsumed by your return value mean that you need to get rid of that linear variable and it's kind of subsumed into this other one that you're returning?
Could you say that again? So we're, with ys, you saying we consume it, and then we also...
Right, like, could you preserve it? Because it's being used in our return linear variable.
Okay.
Because you're going to hold on that memory anyway, so you don't save anything by marking it as linear.
Oh, right. So we're, I think I see what you mean. So this, like from the perspective of the caller, when I have something like this, ys is being preserved because it's being passed to the caller, right? Am I missing the question?
Well, I mean, with the linear types, it says you can use a variable once and only once,
Exactly.
right?
Yeah.
So, with this, like, the data that's in ys is now necessarily being subsumed into the return of append.
Yeah.
So, if we have a reference both to ys and to the return of append, then we could use the data that's in ys twice if we keep both of those around afterwards.
I see. So, like, if you had something like this, right?
Yeah, there's no cost to that.
Yeah.
You still have the y variable because you might want to use it for some reason, whereas keeping the x's around, there is a cost for it because you just made a copy of all of them. And by the way, does this let you bang the tail pointer? I mean, you didn't write it that way, but could you go find the end of xs and just say, I made this a linear type, so I don't want to, I'm just going to go flip the tail pointer to point to ys, and I don't have to like garbage collect that.
You could do that, actually. There's a much more verbose example essentially accomplishes that.
You don't have to write it.
Yeah. Oh yeah, go ahead. Yep.
I just wanted to mention one thing, which is that if you look at something like clean offers a way to sort of merge the sort of notion of a data view type and a data type that you have there.
Oh, okay.
The sort of the uniqueness of a type is actually an attribute you can talk about and quantify and take the least upper bound of between things. So you can actually build something like dupe, which will take a t, will be back a pair of t's, but it can take a linear, it can handle appropriately the cases where t is linear and not, and vice versa. There's a bunch of things that
So you wouldn't need to duplicate in that case, like
yeah,
nonlinear t and linear t.
4 different append functions
Yeah.
and 2 different lists and
all that. Okay, that seems interesting. So here's like that's with like append to consume them, both there. The slightly more, obviously, tail recursive way is given here, and to just kind of describe how you can consume like the data type as you like do pattern matching. The tilde is basically accomplished like that. So this is how you avoid introducing memory leaks. So actually, nil is a bad example because like empty constructors like that, I think, are just represented as just like tags. But like here's a good example where we have a constructor and we haven't explicitly freed it. So if I were to type check this code, or try to, I would get a wonderful type error where it says that XSS needs to be preserved, but instead it's consumed. So in order to send, oh no, I don't actually think that's the most, the best one. The very last one here says XS needs to be consumed, but it's preserved instead. And since we did pattern matching on XS, it sees in this case we did not consume it, so that, and then that violates our, what we stated about XS here, which was that XS must be consumed. So we have to go back and consume just XS. And then once we do that, we get good type checking. And so at the bottom, if we do just the same example code that we had before, where we just have two two lists of 10,000 length and we append them together, we get a very different profile in the memory that's used. So instead of about 600 kilobytes, we only use 468. And then at the end, since I did have that call to list free, all the memory goes down to 0. And this is all done with valgrind and massfit, just as a demonstration of all this being used up. So what this demo is supposed to highlight is that, or intends to highlight, is that you could use like linear types to enforce some resource constraints that you would like to put into your programs. And we especially want to try to explore this in embedded code for like microcontrollers and operating system kernels. And to that end, we've been working on code for like running ATS on Arduino boards and trying to get an ATS library going for like making kernel drivers, which is difficult because the Linux kernel is huge now, or it's been huge for a long time, but it's very difficult to keep up with all the changes there. So, and linear types are a very important part of that. So, are there any other questions about that? Yeah?
So you have something that takes a look at all of your linear types and figures out that the maximum amount of memory that this can possibly use at any point is this amount, and that's less than our target goal.
I would love to build a tool like that.
Okay.
There's, I think we had I forgot where he's from. I think Jan Hoffman from Yale. He's done some really cool work with like doing ML programs, like worst case runtime for ML programs, and not just runtime, also like some stuff for like power consumption, even memory. Like there is a good example of how you could measure possibly the power consumption for like a simple reactive system. And kind of the work that he was doing there seems really, I would really like to try it out for ATS, because if you have, right now with linear types, we're kind of, it's not a very quantitative tool, right? Because we say, this VT is free, the list is free. In ATS, we can get more specific by refining the list type further to maybe include the length, where n could be some natural number. And so then you could reason that, oh, well, at that point, n, like a list of length n has been consumed. Like, what does that mean in the total heap? And I'd love to explore, like, to try to build off of this and try to get actual, like, an idea, maybe how much memory did this program use in terms of, like, the lengths of the lists that it used, which would be, I think, kind of cool.
Yeah.
Do you have a notion of affine types as well, or just linear types that, like, possibly consuming this thing, but not necessarily?
Possibly. So my answer is maybe. There's a type that you could do, like possibly. I think so, but I think it's a cheat. I don't think it's very good.
Consumed no more than once, rather than consumed exactly once.
Oh, okay.
You're forcing consumed exactly once.
I don't think so. The only way I could think where you could even try to express that is that you have like a return type called opt, and that has maybe a proposition, which might be a return value that could indicate that your value was freed or consumed, used. And then by checking that value, you could turn this into like your item again, in which case it wasn't used, or have it be consumed. But I don't think that would really be affine types.
Okay.
I'm not very clear on affine types. That's it.
All right. I'm sorry, just to clarify affine versus relevant.
Yeah.
Basically. So when you say that you have like a linear type, you're saying that you can't use it twice, right? You can't take A and give me A and A. And you also are saying that you can't not use A, right? Those are the two properties. One is contraction, duplicating it, and weakening is the dropping it on the floor. So an affine type system disallows contraction but still allows weakening. On the other hand, a relevant type system allows contraction but disallows weakening. So you could use it multiple times, but every time you kind of give somebody a copy of it, they must consume it.
Okay.
Those are I just figured I'd clarify the distinction where affine comes in. There's other points in this design space, like if you look at Clean, they don't actually have linear types, they have uniqueness types, which are a little bit different. They say I haven't contracted this thing yet. I haven't given anybody else a copy of it, so therefore you can edit it in place.
Okay.
Whereas a linear type system is saying, you will never contract or weaken this thing ever again.
Mm-hmm.
Right? So that's forward facing, and uniqueness is sort of backwards facing. And that's one of the things that enables them to put parametricity on their sort of unique, whether that means unique.
Okay. Well, thanks for that explanation. I love that. Any other questions? All right, thank you.
So do I have sound on this?
You should.
Cool.
I think if not, you can mic the laptop maybe.
Oh yeah, that works. So hi everybody, I'm Kenny Foner. I'm from Brandeis University. I'm a senior there for one more semester. Just finished my finals. And today I'm going to be talking about a
Same sort of thing I run into.
it jumped some of the windows over to different spaces, so now I need to find where they live again.
Well, we know what movies you like.
I think that was intentional.
That's part of the presentation,
Ah.
so sadly, I've given away part of the joke. I was talking to Josh Koff about possible titles for this talk. Originally, so one of the, there's an old joke that there are two big problems in computer science. There's cache invalidation, there's naming things, and there are off by one errors. Today I'm having a bit of a problem with naming things, because initially I called this library Midas, because the point of the library is that I want to be able to manipulate things using mutable state and reference equality, and then eventually freeze that into some immutable representation of what the final result is. You can already do the mutable state part with the ST monad, but what the point of this is that I'm bolting on a notion of optional reference equality so that we can actually say, okay, this pointer is equal to that other pointer. And then at the end, what we get out is a pure value that we can treat like any other Haskell value, as those of you familiar with the ST monad would recognize. So initially I called it the Midas library because the myth of King Midas is that he had the touch of gold. He would touch anything and it would turn to gold. So the idea is that the dirty real world of mutable state could be transfigured into gold by means of this. But then we started talking about the possibility, I named one of the functions freeze. So then we were thinking that it would maybe be more like this, except I don't have sound, but you get the idea. But then I started thinking to myself, wait a second, I don't actually know what to call the stuff that I'm manipulating that before I freeze it. I don't really know what this substance is that I'm playing around with my hands. Am I going to call it snow? What am I going to name this data type? Is it slush? So in the end, I came to a completely different metaphor, which is to say that this library is now called Data.kiln, because I'm playing with clay, and then I'm going to bake it into an immutable data structure. So with that out of the way, I'm just going to walk through how this actually works. I'm just going to show you the code, because it's quite short and simple. So first I define a new monad, which I'm going to call the squishy monad. And the squishy monad is a wrapper around the ST monad. And so for those of you not familiar with the ST monad, this is actually a trick using phantom types. So the ST monad has this extra type parameter called S that tracks the state of the thing that you're manipulating. So what this means is that when you run something in the ST monad, the action that you run has to be something that is for all S. That is to say that it can't mention S in its return type. So all of those mutable references that are produced that have this state tag S, when they're kicked out of the end of the you can't get them out of the end of the computation because that would violate type safety. So as you can see, the signature for squishy for run squishy rather, has to follow the same pattern as well. So I'm using rank-in types to say that I have to take for all S squishy SA. I can't actually talk about S in A. So it's just it's just the ST monad wrapped with a state of IDs. And for me, ID, I'm just using ints because why not? And then, so here's the first trick that I think is mildly interesting. I define this new type identifier, which is just a wrapper around ID, but it has a phantom type S. So what I'm saying by this is, okay, so I've got this state of IDs, but I want to say that every identifier is going to be globally unique within each one of these computations. But if I leak them out of the computations, then I could produce an identifier in one of these computations and move it over to another computation, and then all of a sudden I've lost my global uniqueness property. And that's terrible. So instead, I'm tagging them with this S state, and everything that's tagged with this S state can't possibly be returned from my computation. So there we go. I can do all sorts of fun things with unique identity, like defining this distinct type. So distinct is fun. It's just an A paired with an identifier S. So what that means is that in order to produce a distinct something, I have to do this action, this distinguish action here, in the ST monad, in the squishy monad rather. And all that's doing is it grabs a new identifier off of my identifier state or stream or whatever, and packages me up a new distinct value. But because this is the only way of producing distinct values, I'm guaranteed that every distinct value has a distinct identifier associated with it. And what that means is that I have a notion of reference equality, sort of, if I package up mutable references inside of these distinct packages, then all of a sudden I've got a pointer which is pointed to a thing that I can change, and I can ask, are these two pointers the same? So I can distinguish things. Notice that my instances for eq and ord are only looking at the identity of the thing, because I know that this is safe, because I can't possibly have two distinct objects that have the same identifier in them. Because the only way to manufacture them is with this distinguish function, which operates within the monad, and unless I get an integer overflow, which would take a couple hundred years at a rather fast rate, I'm all set. So you can distinguish things. You can then, if you have a distinct value, you can conflate it. And what conflation means is that you just get out the thing that was wrapped with the unique tag, and it is no longer necessarily distinct. Or you can identify them, which means pulling out the identifier. And then I just copy the reference API from data.stref. Importantly, I'm using lazy ST. None of the tricks that I'm going to show work with strict ST. And I actually made this mistake twice. Once when I was first implementing the library, and the second time when I was re-implementing the library, I imported control.monad.st, and none of my code would terminate. And I spent about 15 minutes each time thinking to myself, what is being overly strict? Oh, right, it's because I imported the strict ST monad. So that's all for the squishy monad. Now, what am I going to build out of the squishy monad? Well, I'm going to build clay. So clay is a little bit like what you might be familiar as this fix data type, which takes a type of kind star to star and ties the knot on the type level to get a recursive type. So what I'm doing is exactly the same, except that at each level of recursion, I'm inserting a distinct wrapped around a reference, wrapped around the F, wrapped around another clay. So it goes in a circle, a sort of triangle, in that I have this distinct tag, and then I have a mutable reference underneath that, and then I have my actual F, which is filled with clays, and then you're back to the beginning. So you've got this recursive type where I can mutate any one of these pointers and change what the value is that's stored within it. So I can do all of the things that you expect to be able to do. I can create a new clay. If I've got an F that's already wrapped around some clay, then I can just box it up into a new blob of clay. I can look at what's inside, and that's a monadic action because it could have been mutated. I can modify it, I can write to it, I can ask what its identity is. But then, what you're all waiting for is, what do I do with clay? Eventually, after I'm done sculpting something with it, I kiln it. And I learned that kiln is actually a transitive verb. To kiln something is to put it in a kiln. So I'm using this. So when you kiln a piece of clay, what you get out is a squishy action which returns a hard, immutable, fixed G. So I'm actually feeding in an extra parameter that's a natural transformation from F to G that gets threaded through here. But what's neat about this is that I only traverse this structure once. Because I know that each one of these pointers is tagged with this unique identifier, I can keep track of all the identifiers I've seen so far and use that to tie the knot, so that I'm not doing this infinite traversal along this possibly cyclic graph, but rather I'm just traversing every node once, and then handing you back something that's actually cyclic. So what's going on in this function is I've just got a state, and this type annotation is optional, but it's just to sort of elucidate what's going on, is I've got a state that's got a map from identifiers to my end result, and then so what I'm doing is, at each step, I look up, is the identifier already in the map? If so, then I just return it. So that's right here. And this is using some nice little plumbing from control.monad.ifelse. It's got lots of little combinators for doing monadic if statements and stuff like that. And then, if it's not in my map, well, I've got to bake it. So I traverse the entire structure, which has to be traversable. Well, first I read out a structure from my mutable reference. I traverse it with this kiln. You know, I don't know what the metaphor is, but I move it around inside the kiln until all the parts are baked. I transform it into, I guess I could call this function glaze. I transform it into my final G, and then I've got it. It's baked. But I still have to insert it into my map. And so this is where the laziness of the lazy ST-monad comes in, because what I've actually got here is a thunk. And so I can get a thunk corresponding to the baked form of something, then insert it into my map of identifiers, and that's why this actually terminates. Because down here, I'm just saying modify the state to insert the baked thing at this identifier, and then return the baked thing. So kiln, then, just takes a traversable thing and kilns it with the identity glaze, I guess. And then run kilning with and run kilning just take an action that produces a clay, run it, and then bake the result, kiln the result. So that's it. That's all you need to play around with mutable state, reference identity, traverse the structure only once, and hand you back this lazy cyclic thing. So, how am I doing on time, by the way?
You got a good 7 minutes.
Oh, cool. So, some examples. This is just a little function that applies a function underneath this compose functor. So, compose is from data.functor.compose, and what that just gives me is, if I've got an f of g of a, then I can wrap that up in a compose, and that gives me a compose fga. And it's a nice way of constructing these kind of structures. So, how about singly linked lists? What about mutable singly linked lists? Let's call that our clay. So I've got this MSLL here that's a clay S, and then the functor that I'm actually using is the composition of a pair of A and maybe, and that's where the fixed point gets tied. So I've definitely got an A, and then maybe I've got a pointer to some rest of the list. And then a non-mutable singly linked list is I'm defining just as being the same as mutable singly linked list, except instead of using clay S, I'm using fix. So notably, these are non-empty singly linked lists. So I can const something onto a singly linked list, and then to those of you familiar with Scheme, these names will sound familiar. I can set car and set cooter. Which is to say, I can set the first item in one of these pairs of a thing in the rest of the list, or I can set what the rest of the list is. So one of my examples is that so A is const the character A onto nothing, B is const B onto just A, and C is const C onto just B. So this should go CBA. But then I tie it around in a circle by mutating A so that it points back at just C. So it's a cycle. And I defined this little utility function that takes one of these SLLs and transfers it back into a regular Haskell list so I can use the list library. So if I say SLL to list of list 1, this will give me a string. Of course, this is going to be an infinite string because I deliberately tied the knot, so I'm just going to ask for, say, the first 10 characters of it, or the first 100, or you get the idea. So you can do singly linked lists, but what about something more interesting? So here I'm defining the type of a graph with labels of type N on nodes and labels of type E on edges. So this is sort of parsing this out because it's all prefix and silly. What this really means is I've got an N, that's my node label, paired with a list of pairs of E and pointers to more of this kind of structure. So I can generate new nodes, I can generate new empty nodes, I can read nodes, I can relabel nodes, I can edit edges, I can add edges. And you can keep defining all of these like domain-specific combinators for whatever type you're talking about, just in terms of the functions that you have in Data.kiln. So in the end, I can generate a graph. So I'm just saying A, B, C, D are all empty nodes with labels that are eponymous. And then I can add edges to the graph just by connecting the two together. And I can return A. And if I ask for graph 1, it's going to spew out a bunch of stuff onto my screen because this is a very cyclic data structure. So that's about all I have. I welcome questions at this point. Yes?
I have a couple of observations for you. So I was just going through the code. One is you're using a ref type, which is just like a wrapper around the ST ref.
Mm-hmm.
That could have, I have like a package for like monad ST that would just let you use the existing ST ref as your graph.
Oh, really? So I would just instantiate monad ST for this new type? Oh.
For your monad. And then that brings me to the next observation, which is that we can kill the monad entirely.
All right.
And this requires a bit of a jump though. And that is that right now what you're doing is you need an ID supply in order to build the map at the very end, in order to fire your kiln, right?
Exactly.
But we can kill that. And that relies on a paper that Fritz Henglein did he wrote the paper, I think, in 2010, shopped it around for a couple of years, and finally released it at IFL 2012.
Is this observable sharing?
No, this was the paper on generic top-down discrimination for sorting and partitioning in linear time.
That sounds fascinating.
And it's a lovely little paper. It's actually not a very little paper. And it shows how to do all sorts of crazy things that you would think are impossible. For instance, if you tried to build a data structure out of just the ST refs give you the notion of comparing them for equality, right?
Mm-hmm.
They don't give you an ordering.
Right.
If you tried to fire your kiln without an ID supply, using just that notion of equality, it would take you ON squared in the size of your structure.
Exactly, yeah.
Okay? It actually takes you theta n squared. That's a lower bound, not an upper bound.
Right.
By adding an ID supply, what you've done is you've made it possible for you to do it in n log n.
Mm-hmm.
It's possible to do it in n, and that's the interesting result of Henglein's paper. And what he does is he provides a sort of generic discriminator type, which is basically I'm going to take a list of A's and B's,
Mm-hmm.
paired,
Mm-hmm.
and give you back a list of lists of B's. clustered by A, right? And he does a bunch of machinery to make this work sort of radix style when you're working with integers and the like.
Okay, sure.
But the problem is you don't really want to treat your ST-refs as integers, right? Because what you're doing is you're giving people the ability to distinguish, well, if the ID is less than 5, do something different.
Right, and we don't want that. Yeah.
And so what he captures is the notion that what you really need is the ability to distinguish which ones are equal, kind of all in a batch, rather than the ability to do pairwise equality comparison.
Yes.
And by making that subtle distinction, he's able to blow everything out into linear time by playing games that are like doing the radix sort tricks, without actually sorting and without actually leaking any information on what the IDs are.
So then you can just use the notion of equality for ST-refs.
Yes. So what I've been building is a package. It's not yet done. I literally started it yesterday. And it implements Fritz's trick. And it's on my GitHub account under discrimination. But by using it in this context, you should be able to get your kiln down to O.
Awesome.
And we can talk about that offline. But I figured, and it would also let you get rid of the ID supply, which would let you move the whole thing to ST-ref, or to ST and ST-ref, and you'd be able to kill the monad ST thing completely. Exactly. So your package becomes much slimmer, but also much easier to use for other mixing with other purposes.
So faster and slimmer.
That begs a question.
Huh? Okay. My question is, what do you think?
I think that's a great idea. I'll check it out.
Generic top-down discrimination for sorting and partitioning in linear time.
Any question for Kenny, not Ed?
All right. Thanks.
Ed,
Yeah.
do you not need a new prim up for that?
Huh?
Don't you need a new prim
I
up?
do need a new prim.
Okay.
So basically what the prim does is it runs through an array hash. Or it runs through an already forced list of pairs, blah, 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 and then builds a mutable byte array that's been filled in all in one batch.
Okay.
I'll show you. It's not terrible.
All right.
But it can be written with 4 and import mem.
Huh. Oh, yeah, that makes sense.
Okay, let's just see. I just like to go to the stories.
Sure, yeah.
An AV minute here, hold on.
I mean, I sort of scheduled 5 minutes.
Where are those mics over there? Where are those mics over there?
I think they're for mic and muffle people in the room.
Let's see.
I've never used them before.
Have they ever been? Is this the same room we're normally in? I don't even know.
They've like upgraded it a little bit. It is.
It's the music.
Here's something. Hold on. I'm not hearing anything on the one channel. Okay. Let's see if my play function works any better. It does. Okay, I'm Tom Tishner. I work at MHE at McGraw-Hill Education with Seth and Tim and Eli who have come tonight. I'd like to thank Seth for volunteering me for this presentation. There's nothing like a deadline for forcing your concentration. I'm going to talk tonight about a library I've written hacking for the past several years using Haskell to generate MIDI files. It's something that I think a lot of guys have, and girls probably, have worked on. There's nothing special or particularly fancy about the Haskell that I'm going to talk about tonight. But what I'm really found to be a lot of fun is using the Haskell programming techniques to abstract musical structures and then basically to hack on music to abstract the underlying organizational concepts, or turn those into parameters that you can manipulate programmatically, and then to push into different corners of musical organization to see experimentally what stuff sounds like when you do things that might be difficult with traditional notation or traditional musical performance. Tonight I'm going to talk about really the simplest of all musical organizational structures, which is a canon, because it's really easy to parameterize and it's really easy to boil down into some very concise code. And I'm going to talk a little bit about the canons. I'm going to talk about how I've mapped those into Haskell types, and I have a lot of fairly didactic examples to play as I go along. So, first question is, what's a canon? Everybody knows what a canon is. This is the canonical canon example. Everybody sung it when they were in grade school at one point or another. And it illustrates one of the most attractive features, is it's really quite trivial. When you're starting to program any kind of musical form like this, you come to the point where you have to enter a bunch of data which actually specifies the notes that you're working with. And a canon is great because it gives you a very small number of notes to start off working with that you can then linearize into a more complex texture. So the other thing that's sort of cool about this is that there's all kinds of precedent in terms of using canons for sort of experimental forms, going all the way back to Steve Reich's early loop pieces. If you ever heard his two seminal pieces, It's Gonna Rain, where he recorded a preacher in San Francisco, I think, and used tape loops to generate amazingly complex textures. All the way up through, there was a recent story, I think, in the New Yorker about this guy, Basinski, William Basinski, who does loops, beautiful, long, repeated loops currently. So it's got a lot of background in the literature. The other great leverage here is that Haskell has some tremendous resources, thanks to Hudak for the Haskell package, which wraps a lot of the guts and the details of MIDI formats and music types, and Henning Thielemann, who abstracted that into the sound.midi package, that it's really pretty straightforward to use to leverage all this stuff. What I've done is basically just to wrap a couple of simple MIDI libraries, or simple Haskell libraries, on top of the MIDI package, the sound.midi package. The first of these is just a bare bones sort of encapsulation of basic music types, pitches, rhythms, notes, scales, the sort of stuff that you've got to have in your vocabulary to get anywhere. A couple of simple routines for generating scales so that you can you can abstract motives using intervals against scales. And then a routine to just take the sort of master collection type, which is a score, and convert that into MIDI files. And the great thing about MIDI files these days is you can suck them up into any number of higher level editors, anything from GarageBand or Logic, to compile them into larger, more sophisticated music pieces. And on top of that, what I'm going to talk about tonight really is the canon, which is just a series of successively more general representations of what it is to be a canon, what the actual musical form is. So here's where we start. I mean, a canon is, it's just a simple title. It's a list of notes. It's an imitative distance. It's some instrument that you're going to use to render it, and it's a number of repetitions. And as you can see, when you want to emit when you want to actually convert take the basic type and generate a score that captures all of the voices, it's just a trivial series of a couple lines of code. And you can use this. Oh, sorry, I got to get out of here. To generate, that's not the piece I wanted to play. Right? Exactly what you'd expect. And et cetera, et cetera. With a little bit of manipulation, you can start to play with some of those parameters. So that, for instance, lost my place. Sorry about that.
Command L, I think, gets you to where you were.
Beg pardon?
Command L, I think, takes you back to where the...
Very, very helpful. Thank you. You get, with a shorter imitative distance, you can start to play with effects that would be a little hard to actually perform, but in this case, it's just faster imitative distance. Moving on to the next sort of level of abstraction, you can say, well, okay, so I have parameterized the canon by virtue of its imitative distance and its voices. Now let's abstract and say we want to have a canon where the voices aren't just repeating at the same interval, the exact same note over and over again, but I'm going to say I'm going to let them vary. I'm going to let them roam across instruments. I'm going to let them roam across intervals, and you wind up with some variations on stuff in the same key, either sort of the pandiatonic sort of style, or you can do it in a more sort of chromatic style. And the other thing you can experiment with is you can experiment with registration to get rather different effects depending upon where the voices fall in their octave disposition. And continuing in the same sort of vein, instead of keeping the voices tied to the same key, if we abstract over different scales and turn the actual tune into a series of intervals, you can get pandiatonic effect, or you can get polytonal effects. Which is a little bit different than just having everything play in the same key. The next stage is to say, well, let's cut the instead of having all the voices imitate, say, at the same exact interval, what if we can actually stagger those and have the voices imitate at different imitative distances? So you can get sort of waves of imitations. And you can do that for different instrumentation as well. And then finally, if we let the idea of all of these parameters vary over time, you could have successive parameterization of each repetition as well. And so the whole point is to really try to explore, given a particular form, if I abstract away the sort of organizational principles and parameterize over those, and I aim for different sort of niches, what kind of effects can I discover sort of in this sort of hacking style? There's a number of pieces that I've worked on this way by way of sort of exploring what I think of as sort of emergent properties of tightly imitative textures, where I think your ear naturally strives for pattern recognition. And so a lot of the time, if you have tightly imitative textures, you'll construct successive patterns through a sort of aliasing process where you hear adjacent tones as linked voices, even though they aren't in the score. Another sort of pattern that follows that model is where pitches that repeat regularly emerge as sort of sustained voices, the same way that you get in an example would be like the Bach violin partitas, where you have where there are multiple lines being played simultaneously by a single instrument. So this stuff is all up on SoundCloud if you're interested in exploring it some more. And that's pretty much my report.
So, do you have examples in your repo that we could go and create our own music if we want to mess around with some of this?
Yeah,
stuff?
all this code is just up on GitHub.
Is it possible to show example of a song at all in code?
Let's see. So this is the util file that I have, and this is the Frere Jacques example. And as you can see, there's a bunch of data entry that just matches up with the motives in the tune. And then the Haskell code that actually emits the MIDI file, this write fs, or each of these routines corresponds to one of those examples. So it's it's really quite simple.
Okay.
Haskell code.
So that's the main file to go into.
Yeah.
Play around and write our own songs and stuff.
Yep.
Have you experimented much, like, I see that you're working with notes and scales here. Have you experimented with chords and chord progressions and things like that?
Only as a sort of emergent property of having multiple lines running simultaneously.
So not explicitly?
Yeah, so for instance, if I go this particular piece, which you'll hear, that there's simultaneously a fast-moving surface texture and sustained voices that are abstracted from that. And they migrate, the harmony migrates over time because those voices are, the pitches within those voices are moving in stepwise motion. So you get harmonic progressions sort of as a side effect.
So is this piece itself open source?
That's a good question. It's up on SoundCloud for anybody to play. I haven't put the actual Haskell file up on GitHub yet. I'd have to find it, actually. I did it like about a year and a half ago.
Have you looked at similar things like fugues?
Yeah, that would be a next step, to have some more strongly patterned musical types to follow up on. The thing that really interests me is where your ear sort of gropes for organization out of a texture that's actually fairly dense and doesn't, and that's the funny thing about that is trying to find the right collection of pitches that have the right characteristics that will create that effect. And I wish I had like a formula for that, which I haven't figured that out. Yeah,
Are you familiar with Steve Reich's piano phase?
yeah, yeah.
Can you do anything like that with this, like varying the speed of repetition?
Yeah, yeah, that's, so one of those variations where the imitative distance changes voice to voice is a little similar to that. And also the final example where there's a canon where you actually would schedule all of the successive transformations. That's the way that you would achieve the same effect as successively lengthening the imitative distance between voices.
Oh, I see.
Yeah, yeah, that's yeah. The thing that amazes me about that is that those are actual performers that are doing that.
I know,
You know.
it's just unbelievable. I don't know how you wrap your head around playing like 10
Yeah,
BPM off of someone else.
Yeah, I agree with you. That seems quite amazing that people would really be able to perform that. Yep.
So that was quite a list of I mean, the long list of files that you were looking for was pretty extensive there. Did you have to experiment to come up with each one of those? You know, I mean.
So I go. So the thing that's been a lot of fun about this is, I do the Haskell until I'm sick of it, and then I do the music until I'm sick of it, and then I do the Haskell. So go back and forth, right? And a lot of the music, a lot of it's really easy to generate total crap when you're doing this, and I've generated a lot of it. And it's sort of interesting too, because your ear is the ability of your ear to abstract structure out of music is quite extensive, but it has its limitations, right? And so you can skate over the edge of that really easily.
I'm just imagining. I had a project once where it involved, because I was lazy and the worst sense of it, where I just manually changed some constants and recompiled and redo something. It's a long cycle between evaluating successive drawings. I finally got to the idea that I just allowed command line parameters that would go a lot faster. So just to take this example a little further, if you thought of the idea of maybe constructing like a virtual console with some virtual knobs that would control the different parameters so that you can very quickly do your experimentation.
I think that
to write out your data set.
if you had like a sufficiently abstract framework for doing that to start off with, yes, that would be great. My problem is that so another example, I have a piece up on SoundCloud that's called Click Track, where I got interested in Quick Check actually as a mechanism for generating random data and then parameterizing that into. Actually, I was interested in growing the texture using Fibonacci series, because if you have linear progressions, your ear quickly gets tired of listening to the same rate of change. But if you have an accelerated rate of change, it actually is more intuitively accessible. And there's no way I could have figured out ahead of time a sufficiently abstract set of knobs to twiddle for that. So it's sort of fun because the musical sort of substrata in the sound.midi file is very general. So there's a lot you can do, as long as you're starting off with the idea of a pitched, of a normal sort of classical notation environment.
I just wanted to say something else to that point. There was Data.kiln just released a little modular synth in Haskell. He just put online, I think, a couple weeks ago. But the interesting point was he sat down and he used Gloss to build the user interface for it, and then he has this thing sort of dynamically compiling the back end for his synths.
Okay, so
I figure you can at least, if you're interested in trying to play around with the user interface approach.
Yeah, well, there's
he gets a lot of mileage out of using Gloss to do his sort of bells and whistles.
Well, there's the whole live programming thing too, which is, that's interesting because it's very seductive to build a piece by successive layering, growing it and coming down, and to do that interactively is like a whole performance skill, really, which I'd like to learn, but I don't really possess at this point. Okay, thank you.
I was originally not going to use it.
I hope so.
We're going to move on a couple of unrelated things here real quickly. Soon pop up. All right. I can see a thing. So I mentioned earlier during Kenny's talk a little library for playing around with discrimination, which is based on Fritz Henglein's toy. And it's really based on an alarmingly simple type, this discrimination thing. So basically the idea is, what you want to do is you want to run down this list of pairs and give me back all of the things grouped by whatever property of A that we wanted to talk about. And if you have an ordering, you can do it more efficiently in some cases. But even if you don't have an ordering, even if you only have the ability to break things out into equivalence classes that are not relatively ordered, you can actually get a result that doesn't actually depend on the relative order, but can take advantage of the fact that you can temporarily assign an order. And that's where you get your linear time.
Okay,
So I just figured I would mention that in passing. And then Dan had mentioned earlier that you need an extra prim, and it's fairly horrible. But that lets me walk an already forced list of pairs of I/O references and values, and get down to the mutable variables inside of there and distinguish their local relative addresses within one sort of garbage collection step before the garbage collector can step in and move them, and then scribble out the addresses into a mutable byte array that I can then use to do the shuffling. So you can do it. It's just horrible.
Okay.
So I'm going to package that up.
Right.
So that nobody else ever has to do this ever again. And so that brings, and the other thing was the paper itself, I mentioned briefly, was this paper, Generic Top-Down Discrimination for Sorting and Partitioning in Linear Time. I figured I would throw it up on the screen so people could actually see what the heck I was saying, because it's an awfully long title for an incredibly good idea. Okay, so this notion of packaging things up is a lot of what I'm all about in the Haskell community. And it brings me to a very, very short, almost rant, I guess, to end this lovely day full of talks where people put far more thought and consideration into their material than what I have today. The concern that I have is that it's very easy for people who come from other programming languages into Haskell to fall into a trap, okay? And that trap is in many ways just the very notion that you should try very hard to encapsulate all the details to protect your users from themselves inside of a package, okay? And I'll showcase an example here as I after I get a chance to kind of rail a little bit here. But in other languages, when you're actually working with, say, a class, and you go to say, well, if I were to extend this class, I am the gatekeeper of this class. I own the source file it's in, so I can use protected and private members and do these things to prevent people from screwing up my invariants inside my data type. In Haskell, there are some problems with that notion. When you're working in like C++ with that approach, you have the benefit that if they wanted to extend the class, they were going to have to go edit that source file anyways, right? There was one place to change it. But in Haskell, we have type classes, and type classes aren't necessarily defined paired up with the data type. You can define a class later that extends an existing data type. You can extend int with new functionality. If we hid all the details of int from you, you might not be able to express all of that functionality in the same asymptotics as you can if it's exposed. Now, the danger of this is, of course, you now have to worry about the fact that anyone on the planet could go through and violate any one of your invariants. And that's something that to someone like me who's really obsessed with correctness and making sure that things are packaged in the right way, I have to live in this sort of very uncomfortable space. So I figured I would share my discomfort with the rest of you. But there's not a easy sort of, tit for tat kind of one-for-one trade-off here. Okay? In one scenario, you have users can come along and they can try and use your library. This is where you encapsulate things. If you use your library, if you build a library and you make classes where you, don't expose the members of the classes so that the user can't, let's take an example. Parameterized texture target T is a class. What does it do? I have no idea. I can go dig in the source and I can find that there's all these methods. But the moment I need to make a new instance, I'm dead in the water. The moment I need to use the abstraction that the user has given me to do something that they didn't anticipate me using it for. Maybe I want to talk to another package, like OpenGL raw or something like that, and I need the GL enums and I'm going to get out of this thing. If I don't have access to them, I just have to throw away all the code I've built using this library and replace it. So I have 2 or 3 very unfortunate options at my disposal. I can send a patch to the library author and hope that I get a change within the next 6 months. That's what I've done here. Or what I can do is I can stop using it entirely or bring it entirely in-house. I can make my own custom local copy of this. This is what, a lot of, like Standard Chartered has a bunch of things behind closed doors, as far as I can tell, that are forks of open source projects where they've had to tweak things slightly to fit their domains, and they haven't pushed the changes back out. Which is kind of bad for an adoption and sort of layering and building up a large community of libraries. Or I have to just say, screw it all, I'm going to build a new package. And if you know me, that's generally been my solution. So I ran into this problem, and I'm using the OpenGL package in particular. I apologize, Jason and Sven, if you're listening online. Because I was using the OpenGL package because I've been playing around with graphics in Haskell lately. Because I want to be able to talk to some of my old game dev buddies and try and convince them that Haskell is a good place to do work, right? And I was trying to use the OpenGL package to do this. And it was routinely the most frustrating experience that I have ever had writing Haskell. Again, sorry, Jason and Seth. And it's largely because of this issue. This notion that we're going to try and protect the user from themselves. Okay, so there's an OpenGL package, and then there's OpenGL raw, which gives you theoretically lower level bindings. But I can't move from OpenGL to OpenGL raw cleanly. There's all these abstractions in OpenGL that I can't borrow. I can't. When I need to do one extra thing to a texture that they didn't anticipate in the OpenGL raw in the OpenGL package, and I wanted to transition to call the OpenGL raw function to do it, I have to throw away all uses of the higher level abstractions, because they're not accessible to me. They're not abstractions that are for me. They're abstractions for the author of the library. Okay, so building things that I fundamentally can't build upon is a really troubling thing to me. Okay, so I really wanted to sort of challenge the notion that encapsulation is generally a good thing, especially when you move into a language like Haskell, where users are going to be routinely extending the scope of what it is you do. So always, please, always assume that somebody's going to come along with a use case you did not have in mind. Because eventually I will use your library. So to that end, I turned around and I was playing around with this OpenGL and OpenGL raw binding. And I finally gave up. And so Polarina, Gabrielle Arthur Pedersen, had put together some bindings for SDL2 that were really pleasant to use. And I really liked her approach there and started sending some code to improve the process there. And then she reached out and had built some OpenGL bindings, and I sort of mashed those together with some of the guts of OpenGL and spent about a week and a half and released the GL package. And GL is currently the largest package on all of package by I think a factor of 5. It's all of OpenGL from 1.0 to 4.5, every extension that has ever been provided and documented by anybody. And if there's one that you know of that I don't have, let me know and we'll add it somehow by hook or by crook. So it does all of OpenGL for desktop, it does the mobile profiles, it will soon do WebGL and all the WebGL extensions as soon as allowed to get some time to work with me on that. And that will let us turn around and in Haskell start packaging up anything you want to do with OpenGL to run on Windows, Linux, and Mac, as well as on iOS and on Android, as well as in Chrome and in Firefox, and recent Internet Explorers. So at that point in time, I can at least start talking to some of my older game dev buddies and start saying, hey, look, come on into Haskell. We have tools that are more portable than the ones that you have in other languages. We can start making a case for the language on the merits of it, not on, it's more correct or anything. Just, hey, look, we have things that we can just pick up and build this stuff and run almost everywhere. So that's the gist of it. I think, in general, even if you don't want to expose it through the public API, if you can just make a .internals module or something like that, say that it doesn't apply to the PVP, that if you depend on this module, here be dragons, and you'll have to change every time I do a minor release of the package. But I think the failure mode there is very different than the failure mode for the first case, which is I have to stop work. I just can't think a thought anymore. And that's a really troubling place for me to wind up being. Right? In the other scenario, I've loaded the gun, I pointed it at my foot, and I pulled the trigger if I violated your invariance, right? I created the problem, and I can fix the problem. In the mode where you protect me from myself, I can't solve anything. And so that's my rant. So, thank you. Any questions?
So is this about expert users versus novice users? Like,
I don't think you have to choose. I think honestly you can provide a very nice public novice API. It's just make sure that you have some kind of escape valve, even if it's just a little .internals module that you don't by default give anybody. I'm not asking for you to say screw those the newbie users. We don't need them.
So it's kind of like why Haskell provides the unsafe stuff.
Yeah, exactly. Eventually you're going to need it. Yes?
Are you saying you should just export all your functions?
Even if I'm sorry, am I saying that you should just export all your functions? I'm saying that at least if you make a bunch of, especially like data types or classes, they should probably be exported somewhere, if not through the primary public API that you're going to expose to users. Right? If it was an abstraction that was useful to you, it's probably an abstraction that will be useful to somebody who wants to build upon your work. Yes?
Stupid question. What actually, I didn't understand the technical limitation that stopped you from proceeding in your showcase.
Sure.
Could you show an example or something?
I could. Let me see if I can get the... all right. Let's see here, if I can do this.
I think I ran into the same problem.
Come on. All right. So if we go back to OpenGL, we have this notion of a texture target. All right. And in this notion of a texture target, let's see if I can find a parameterized texture target as a class that we have available to us. We can talk about 1D or 2D or 3D textures, all these different things. Okay. And so you can say, I want to load a texture and tie it to this thing, or I want to change some property of some attribute of a larger set of resources on site in the OpenGL library. Now, the OpenGL package turns around and makes up its own abstractions for all of these things. They don't exist in the core library. Actually, if you look at the GL texturing machinery, I don't know, GL compressed text image 1D or something like that. This is what you actually get from the library. You get a GL enum, and it can be one of these values. GL enum is just this gigantic sewer worth of possible values, right? And so they decided what they were going to do is they were going to enumerate all the things that were possible for individual uses of this thing and make a data type and protect me from myself. Now there's some problems. The actual set of parameters that you can send to almost anything depends entirely on what set of extensions you have loaded. Because a new extension can add a new option for any one of these functions. And they often do. So you almost always universally have to make some kind of escape valve in whatever data type you're going to offer the user that you're going to try and put in as a proxy anyways. So with the GL package, what we wound up doing was building little pattern synonyms to get at the enum. And this lets me match on them in both pattern position and in value position. So this is a new feature in GHC 7.8. We added pattern synonyms. This has a couple of benefits. One is that you can Google for this. The made-up Haskell name is completely ungoogleable. The only thing you'll find is the Haskell documentation, which is riveting and awesome. I've learned so much. So here I can at least go back and I can find out, what these things are. I can Google for it. I can find rafts of documentation on the internet. So I wanted to make sure that when I was building my low-level bindings, and I built low-level bindings, that you could actually find out stuff about. And here, we actually can scrape through some random XML documentation sources and things like that and peel out what the parameters are and what they mean. I wanted to try and do something to try and make this a little bit more accessible. And we hyperlink out to the actual RFCs that specify all of the individual extensions that we turn around and document. So the particular example here centers around this notion of, hey, look, I want to talk about a texture target. And in the OpenGL package, they've abstracted this. They made little classes. They made a little class that lets you marshal it out to that GL enum type. And then they hid all the details from you. Now this was great, right up until I needed to do a thing that could load or save a texture arbitrarily out to OpenGL. So here I have a project I've been working on called Quine, which is shaders examples. Real-time ray tracing engine in Haskell. Working on getting it suitable for gaming. This is getting faster as I go. And this is actually a quick example. And in there, what I have is the ability to take screenshots and upload textures. Right? And I wanted to solve that problem sort of once and for all because it's just an annoying problem. So we have a library in Haskell called Juicy Pixels. And Juicy Pixels provides a notion of like its internal. It has its notion of what it calls it. I don't remember what they call that. The graphics, pixel-based components and stuff like that for their image types. And so what I built was a small abstraction over what the image formats that Juicy Pixels has and how those marshal to and from OpenGL. And then I started building machinery to let me send all of those textures either to download them download a texture from the GPU like a screenshot, or to upload a texture from Juicy Pixels as a texture. So take an image, load it up from a JPEG or PNG or whatever file format you have lying around, and just please, can you make that a texture for me? I wanted that sort of very easy functionality for moving back and forth. And along the way, I needed one function that wasn't offered by the existing GL package. It was, let me see if I can find it here. The Swizzle LA thing is using it. So I needed to set this texture parameter, how to swizzle the RGBA parameters to say that they should be red, 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 and 1 in order to take a luminance texture and ship it to OpenGL. So in order to properly format all of the formats that are supported by Juicy Pixels, one of the formats is I can give you a grayscale texture, and I should be able to just turn that and turn it into a grayscale. I should be able to take a grayscale image and turn it into a grayscale texture. Okay, and to do that, I have to either blow it out into RGBA and waste 3 or 4 times the memory footprint, or what I can do is I can load it as a single channel texture and then tell OpenGL what you should do is you should treat all 3 of these channels as reading from the red channel. And then when you ask for the RG or B value, you get the red channel. Okay, so this notion of swizzling is something that the OpenGL package doesn't expose. OpenGL Raw does. But I tried originally to use their texture targets. And now I have to stop. I can't use the abstraction. The abstraction is dead to me because it's not exposed to me. And that's sort of the notion of where I actually concretely got stuck.
That's the part I actually quite rock.
So what they have is they have a class, right? And so what I want to do at the end here is, let me look at upload here. Upload takes a texture target, which is a notion that's created inside of QuineGL, not inside of the actual OpenGL package. But originally this was using their parameterized texture target class as a constraint, or wanted to use it. And that worked right up until the moment when upload needed to do the swizzling. But now I can't know what GLenum I need to tell this other package that OpenGL is built on, because the OpenGL package protected me from myself. It hid the lookup for how to marshal that value. So if we go back over here, where was it? Parameterized. I browsed a bit here. Somewhere in here. It's texturing specification. Parameterized texture target. If we look here, the class exports no members, right? So good luck making another instance. But internally, what it does is it says, well, what is the actual? How do I take a T and give me the texture target or the proxy for the texture target or enabling, like what the capability for enabling or disabling this thing is, right? These three members are just not exposed to me.
So if they exported that, would that solve your problem?
If they had exported that, it would have. In theory, I could have continued on using the OpenGL package until the next problem. Now, if you look at the OpenGL bug tracker, I've submitted roughly a dozen bugs over the course of a week. And since OpenGL is a Haskell platform package, those can properly be fixed once a year as part of the release of the Haskell platform, basically. I'm not willing to stop development for a year, because in a year I probably won't care about this problem. That's basically where I'm at. So it took me a week and a half to write OpenGL bindings that never get in my way ever, and can't, versus stopping work for a year. And those were the two failure modes that I had available to me. I could either fork OpenGL and make it completely impossible for my users to install, like my customized version of the existing OpenGL package. I would have to have given up all of the Hackett ecosystem. Or I can build a completely different package that just tries to make it so that I'll never run into this problem again. And so I chose to do the latter because I didn't see any sign that it was ever going to get any better.
I by no means criticizing your choice. I just wanted to understand
Yeah.
what the problem was.
Yeah. So that is sort of the nature of the problem, is that I was running headlong into a wall over and over again. And now the other thing was I actually wound up needing OpenGL 4.1 features, and the OpenGL raw library only supported 3.2 or 3.3. So I wound up having to do it all anyways. So in the end, I was probably going to wind up doing what I did, or having to dramatically extend the scope of the OpenGL raw package, which is part of the Haskell platform. Yes?
Is there any of your game dev buds interested then?
I'm working on it. So I figured there was. So this is a huge tangent from my actual rant. But the sort of notion that I had was, if I wanted to try and fix up Haskell game development, I needed three things. One was bindings that could say all the things. You couldn't get stuck. You had to be able to say all the things you can say on another platform, or you're just going to wind up being dead in the water. The second thing was I wanted it to actually be a more pleasant experience, so I wanted some stuff that could actually do high-level OpenGL things. So one of the things is, like, in OpenGL you can talk to shaders, and in shaders you have these things called uniforms or uniform blocks, where I can where you basically can copy and paste a structure from C over into shaderland, where it can be accessed by the whole shader pipeline. And that's historically, like, the OpenGL package and the OpenGL raw package just don't support them. They're a relatively newer concept, etc. So I sat down and I wrote a whole chunk of code using GH generics that can take any Haskell data type and just serialize it back and forth, for instance. And that starts to make the experience of working with those things more pleasant, or at least in that case catches up to what you can say in C, which is you can just write down the struct using some little fancy alignment rules, and you can then just marshal it back and forth. So I needed to, A, not to get in your way, B, be more pleasant to use, right? And the OpenGL package was starting to fail on that front because we use monad transformers in Haskell, so you start decorating everything with lifts all over the place. And it just becomes noisier. So, like, if one of the benefits of Haskell is the clean syntax, decorating everything with lift $sign for every line of code that's talking to OpenGL was starting to kill that benefit. So I lifted everything into Monad.io, for instance. So those are the first two premises. And then the third one was I need a reason that someone who would not normally write Haskell should go look at the code to try and figure out what the heck we're doing. Okay? Because otherwise all we're going to do is we're going to pick up the people who come along to Haskell sort of by Brownian motion, who like here, well, there's a user group, I'll come. Or that like caught that John Carmack gave a keynote at QuakeCon. Well, he gives the keynote at QuakeCon every year, but he gave a keynote and he talked about the fact that Haskell and Lisp were interesting. And so that's why I sat down and started building this Quine project, which is to turn around and show that we can do some very interesting things. And if it's interesting and if it's different enough, in order to figure out how the heck it works, you have to actually read the code. So it gives me a reason to make somebody who would not normally look at Haskell read some Haskell. And that's sort of the motivation that I have there. It's not to build the next AAA game title, this, that, and the other thing. It's got to be something distinctive enough in terms of art style and what it's capable of to make someone who would not normally read Haskell. So I haven't finished that leg of the journey, and I may not before I get bored. But I figure along the way, I'll at least get some better tools for folks, and we'll see where it goes. Make sense? All right. Anybody else? Yes.
Are those handwritten or machine generated?
Which ones?
That you're binding to OpenGL?
A mishmash of both. It's mostly machine generated. There's a Kronos XML specification that's wrong. And so we patch it up wherever we have to fix the spec. So we have a parser that uses HXT that does that. So we wrote about 6 modules worth of code, and it generates all 750 modules. And it scrapes documentation sources and pulls all the things that it has to, and we have like a little XML file for that thing, and then we have that we can then upgrade from Kronos, which is actually kind of nice because we now support more OpenGL extensions in Haskell than the big standard C extension wrangler library, right? There's about a half a dozen more that we support than anybody else at this point. They'll catch up almost immediately, but it was 2 seconds worth of effort for us. And so as we work towards OpenGL 5, that's going to become a bigger and bigger thing. All right. Well, thank you.